In this video, we discuss electrical energy and power. So, electrical energy and power. Let us consider a conductor. So, let us consider a conductor here. This is the conductor. If I maintain potential, let us say VA here and let us say VB here. Now, I am maintaining potential VA here and VB here. If VA is greater than VB, then positive charges will go from VA to VB, from this end to that end in this direction. So because of this potential gradient, because of this potential difference, charges go from high potential to low potential, and here VA is high potential, and so charges will go from this point to that point. So we know that the rate of flow of charge is called current. So you can write down that current is equals to delta Q by delta T. Delta Q by delta T is current. So that implies if you wait for delta T time, the amount of charge that goes from VA to VB is delta Q equals to I delta T. So if you wait for delta T time, then amount of charge that goes from this end to that end is delta Q equals to I dt. So when this charge goes from here to there, then what is the change in potential energy of this charge? So let us calculate that. So change in potential energy of this charge is delta Q times the voltage difference between 2 points, that is final voltage at final point minus voltage at initial point. So this is the change in potential energy of this charge, of the charge that is going from this point to that point. So now we know that VA is greater than VB, so when you take this difference you get some negative number. Let us write down the negative number here. So I'm defining the voltage difference VA minus VB equals to, because VA is greater than VB, so I'm writing that as, let us say, V. That's the voltage difference between point A and point B. So if this is point A and if that is point B, that's the voltage difference. So VA minus VB equals to V. So now I can write down here, that is delta Q times VB minus VA will be minus V. Can keep minus here, and that is the voltage. So that is the change in potential energy of charge, delta Q, that is going from point A to point B. So if charges are going from A to B without any collision, let us take this situation. If charges are going from A to B without any collision, if there is no collision, then total energy of the system must remain the same. So if I take total energy of the system remains the same, or the change in total energy must be 0, so that will be equals to delta K plus delta U. So if there is no change in total energy of the system, then delta E must be 0. So when this is 0, then delta K plus delta U must be 0. That implies delta K must be minus delta U. So minus delta U is delta QV. So now you can write down delta K equals to delta Q into V. So this is change in kinetic energy of the charged particle that is going from here to here. But in conductor, charges moves with constant velocity. It means there is change in kinetic energy here. It means that as it goes from here to here, then kinetic energy of the kinetic energy of the charge must increase from here to there, because potential energy is coming down as it comes from here to there. Then by conservation of energy, you can say that kinetic energy must increase from here to there. But in conductors, all particles, all charges at any point will be moving with constant velocity. So it means there will be no change in kinetic energy. So there will be no change in kinetic energy. But if you take the charges are going without any collision, so this must be the change in kinetic energy. But in general, the electrons or charged particles will be moving with constant velocity. You will see there will be no change in kinetic energy. Then what about this kinetic energy, where this has gone? So this energy will appear, this amount of energy will appear in the system in the form of heat. The same amount of energy will appear in the system in the form of heat. So delta H equals to delta QV. Right? So if there is no collision in this system, then electrons or charges, when positive charges delta Q goes from here to here, and you see the change in potential energy is this much and change in potential energy is negative, then total energy must be constant. So the total energy must be constant, then gain in kinetic energy must be equals to delta QV. But there will be no gain in kinetic energy, because charged particles in the conductor will be moving with a constant velocity, that is called drift velocity or drift speed. So because of this, there won't be any change in kinetic energy. So this amount of energy is dissipating in the system in the form of heat. That is this part. So delta Q already we have told that is I delta T. So now delta H equals to I delta T into V, or you can write down Vi delta T. That implies delta H equals to Vi delta T. So this is the amount of heat that is dissipated in the system this is amount of heat, or this is amount of energy that is dissipated in the system in the form of heat. So if you wait for T time, then amount of energy dissipated in the system, you can write down that as, if you wait for T time, so you can integrate. If you wait for T time, so you get amount of heat dissipated in the system equals to VIT. This is the amount of heat dissipated in the system. And this is a conductor. If this is a conductor, you can write down Ohm's law for this. So Ohm's law says the voltage across the conductor is proportional to current going through the conductor. Voltage across is here VA minus VB, that is V. So you can write down V equals to, V is proportional to I. If you remove that proportionality, you get R. R is resistance of this wire. Sometimes we can also write down, instead of writing this wire, I can also uh, mention the same wire by symbol. This is the symbol for resistor, because any wire, any conducting wire behaves like a resistor. So I can write down like this. The same thing I can replace like this in certain cases. So now V equals to Ra. So here R is resistance of this wire, and that you can mention by this symbol. And if V equals to Ri, let us substitute here V. So that implies H equals to, then you get V is IR, then you get IR into IT. So it is I square RT. This is one equation. So similarly, we know I is V by R. So when you take V square by R square into RT, so you can also write down V square by RT. So all are similar equations. So this is amount of heat that is dissipated in the system. So now let us write down, come from here once again. So now you wrote delta H equals to delta H equals to Vi delta T. So this is amount of heat dissipated in the system in delta T time. So now we know that power is defined as the amount of heat dissipated in the system, or you can say this is amount of energy dissipated in the system. You can write down in general, this is amount of energy dissipated in the system, that is Vi delta T. I already used E here, so you can write down some other form. So you can write down even H, no problem here, because I already used E for total energy, but this is amount of energy dissipated in the system. So let us use some different symbol for that. So the rate at which the energy is dissipated in the system is called power, and that is dE by dt, that is Vi. So rate at which power is dissipated in the system is called power, and that is Vi. So you can also write down power as, because V equals to Ri, so you can also write down it as I square R, because I is once again V by R, so you can also write down V square by R. So all the equations are C. So now this is a power and this is energy. So we know the unit for power is watt. Watt is the unit for power, and let us look at 1 watt equals to how many joules. So let us take one familiar unit, that is called 1 kilowatt. 1 kilowatt. So 1 kilowatt equals to 10 power 3 watt. 10 power 3 watt. So now, but kilo, see here, unit for power is, this is Vi, unit for Vi is power, Vi is power, that is watt, and delta T is seconds. Then watt second is joule. Now let us write down 1 watt second equals to 1 joule. So in general, you will be measuring energy in terms of in any electric circuits, you will be measuring energy in terms of kilowatt hour. So let us see 1 kilowatt hour equals to how many joules. So 1 kilowatt hour equals to 1 kilowatt hour equals to 1 kilo means is 10 power 3 watt, and 1 hour equals to 60 minutes, and each minute is 60 seconds. So that equals to 6 into 6, 36 into 10 power 3, and here 1 and here 1, then total 10 power 5, then watt into second, then watt into second is joule. So now that implies 1 kilowatt hour equals to 36 into 10 power 5 joule. This is the conversion, energy conversion. So most of the, in electrical circuits, we will be measuring we will be measuring energy in terms of kilowatt hour. So now where does this power is coming? See here, the charges are going from here to there. As charges are going from here to there, it is the charge is continuously colliding with a lattice point. Whenever it collides with a lattice point, then the charge is losing its total kinetic energy, and total kinetic energy will be transferred to the lattice point. So the energy of the charge is comes to zero once it has a collision. Once it collides with a lattice point, energy of the charged particle comes to zero, and again it gets energy from some external source. So here, this is the power, that is Vi. This power will come from some external agency, and that external agency can be a battery. So the symbol for battery is this. This is the symbol for battery. This is the symbol for battery. So one line and one small line. This is the symbol for battery. And so definitely, as the charges are going from here to here, so to send charge from here to there, some external agency must be there, and that external agency is battery or cell. So now these equations, if you look at these equations, these are very important equations. Let us look at one problem here to give this importance. In case of power transmission, assume that you want to give power P, you want to deliver power P to a device that is at far away from you. Let us say here there is a device, here there is a device, here there is a device. You want to deliver power P to this device from, let's say, from long distance. So to deliver this power to this system, then you must have a connecting wire, because somewhere here you are generating power, then you need to send that power from here to there. So for delivering, you must have some connecting wires. So now assume that these connecting wires are having resistance RC. So because connecting wires may have some limited resistance that you cannot avoid, so RC may be the resistance of this resistor. RC may be the resistance of this connecting wire. Now this is the device to which you have to supply power P, that is VI. So if power P you want to deliver, then I must be current going through this device. If current I is going through this device, the same current must flow through this wire also, because everything is connected in a loop. So you can say that if I is going here, the same current must go here. So if I is current going here, then there will be power loss in the connecting wires. So the power loss in the connecting wire, equals to I square RC. RC is resistance of the connecting wire and I is current going through that. So now from here you can write down that I equals to P by V. I is P by V. I is P by V. So let us substitute this equation here. So you get P square RC by V square. So now power dissipated in the connecting wire is P square RC V square. So now if V square is very less, if V square is very less, or if V is very less, then PC will be very high. So to minimize, because you want to deliver power to this, so whenever you are transmitting power from one point to another point, the power losses must be very minimum. To have minimum power loss, to have minimum PC, then V must be very high, then V square must be very high. So if V is very high, then power loss will be very low. So then because of this reason, after a generation, once we generate power, immediately we will step up the power, or once we develop any signal, voltage signal, then first before transmission we will step up the signal. Step up means we will increase voltage from certain value to high value. Once you increase voltage value, then power dissipation in the connecting wires will be minimized. So to do that, we will step up the transformer. So once we step up the transformer, and the signal will be ready for power transmission. So as I said, an external device is required to maintain constant current in the wire. So that device is called battery, and battery can provide constant, or you can say battery can maintain, as long as you are maintaining that constant potential difference across the conductor, you can able to establish current in the wire, and you can achieve that by connecting the wire by connecting this wire to a battery. So let us discuss what is EMF and what is internal resistance of cell. So now EMF and internal resistance of cell. So already it is clear that to establish current in this wire, let us take this wire once again. So to establish current in this, so you must maintain constant potential difference across this conductor, and to maintain that you need a battery. Let us say this is the symbol for battery. So once you maintain that potential, because assume that these two are connecting wires, these two are connecting wires having negligible resistance, and this is your main wire. So now whatever potential is there here, the same potential you will see here, and whatever potential is there, the same potential you see here. So if V plus is here, because this is the positive terminal of the battery and that is the negative terminal of the battery, so potential at positive terminal is V plus, potential at negative terminal is V minus, and this resistor, this wire has got zero resistance, this wire has got negligible, both negligible or zero resistance, so potential here will be negative. So now potential difference will be V plus minus V minus, so that can be V, let us say that is V, that is the potential difference, right? So let us look at the structure of the battery here first. So say this is the battery, so here I am drawing, this is the battery, and inside the battery there will be two terminals. So one is called positive terminal and one is called negative terminal. So this is called positive terminal, that is called negative terminal, let us say. This is positive terminal and that is negative terminal. And these two, in this we said these two are electrodes. One is at high potential and one is at low potential. Say this is at potential V plus and that is at potential V minus. Even I can write down the values. For example, if V plus is plus V, okay, let us take V plus and V minus. V plus can be some positive number and V minus can be some negative number. So now these two electrodes are immersed in a electrolytic solution. So here you have electrolytic solution. This is the electrolytic solution. If there is no current, if this battery is not connected to an external circuit, if the battery is not connected to an external resistor, then there will not be any current through this battery. So when there is no current in this battery, so the electrolytic solution, the potential at any point in the electrolytic solution will be same. So if electrolytic potential at any point in the electrolytic solution is same, and you find there will be no potential difference from here to there, and the potential difference between this terminal and that terminal will be now equals to V plus, because there is no potential difference in this solution, so you get total potential difference from here to there is V plus minus V minus. So that will be your EMF of the battery. So now you can define EMF of the battery as the potential difference between positive and negative terminal of the battery if there is no current through the battery. So the full form of EMF is its electromotive force. But even though the name is electromotive force, but this is not a force, but this is the voltage across this positive and negative terminal if there is no current through this. So now EMF E is equals to simply, it's a voltage. It's not a force, it's a voltage. Okay, now if you connect this battery to the external resistor, let us say. So now let us take the same diagram here once again, or let us connect here itself. Now I am connecting this one to a resistor. Say resistance of this resistor is R. So resistance means it can be a wire once again. It can be like this wire. For convenience I am taking in this form. So now we know the potential here is V plus and potential here is V minus. So now there is potential difference between this point and that point. Let us write down. Shall I write down here A and B? So there is a potential difference between A and B. So because of the potential difference, then positive charges will go from A to B through this resistor. Charges will go from here to there through the resistor in this way. So whenever charges are going, you can say the rate at which the charges are going is is called current. So the current will be going through that line. So I is the current. So I means delta Q by delta T, or you can say dq dt. So now dq I dt. So now we know it means that positive charges will go from A to B in this direction. Whenever positive charges are going from A to B through this line and they get deposited here. Once they get deposited here, then potential here increases. When potential here increases, if keep on charges are coming here and getting deposited here, then potential of this terminal also increases. Once potential terminal of this terminal increases, and after some time if you see, you find there will be no potential difference between A and B point. If there is no potential between A and B, then you see no current in the circuit. But in case of battery, what happens? Whenever some charges are coming from A to B through this line, assume that in delta t time, in dt time, if dq is charge that is getting deposited on this line, on this terminal, then immediately chemical forces will come into picture, and that chemical forces will transfer the same amount of charge through the battery from B to A. So when charges are going from here to there, and you will see some current, the same, because same, for example, if dq is getting deposited here in delta t time, to maintain constant potential difference, the same charge must be forwarded from B to A by chemical forces. And so whatever you see current here, the same current must go through this battery also. When current is going through the battery material, and battery material itself will offer some resistance, and that resistance is called internal resistance of the battery. Internal resistance of battery, and you can denote that by a small r. That's the internal resistance of the battery. So as I said, electromotive force is defined as voltage across the positive and negative terminal if there is no current in the circuit. If there is current in the circuit, then electromotive force, then voltage across your A and B will not be E, and it will be something less than that E. Let us see what is that. So now you take this circuit once again, then I is current going through this resistor, then current is going in this resistor, and I said positive charges will go from high potential to low potential. So now it means charges are going from A to B through this resistor. It means that potential at A is higher than potential at B. So the potential difference is here V, that will be equals to then current times R times current. This is what voltage across A and B through the resistor. And when you take the same voltage across these terminals of the battery, if you take in this line, then what you will be getting? So now if you are taking in this line, then you will say, then here it is V plus and here it is V minus, then voltage difference will be V plus minus V minus, and that is voltage across these terminals. But current is going in this direction, the same current is going in this direction, and this material is offering R resistance. So it means that there is some voltage in this direction. So that voltage will be your Ri, like this. So voltage across these terminals in this direction is Va minus Vb, that equals to, or V plus minus V minus equals to Ri. And when you compute the same voltage across between two terminals in this, so you get V plus minus V minus, that is what your E is. And here current is coming in reverse direction. So it means that because of this current, the voltage difference between these 2 points will be minus IR, because current is going in this direction. So you get minus Ri. Here also it should be minus IR. minus IR. So now what is happening, let us look at here. So, or I can even the same thing I can write down in different form. Let us see. If this is the battery of EMF E, and you can represent internal resistance like this, internal resistance like this. So this is what your battery, the whole battery I can replace like this. So when you connect this one to an external resistor, let's say R, and this is internal resistance, then current will be established in this, and same current must go through the internal resistance also, as I discussed here. Now let us take 2 points here. You pick up 2 points, A and B. So first measure voltage across A and B in this direction. So now you get VA minus VB. Let us take it as V, that equals to, here is high potential and here is low potential, and voltage across these 2 points will be equals to R times that current. So you can write Ri. So when you measure the voltage across VA minus VB in this direction, so that must be V, that equals to, that will be equals to, say this is, let us take one more point here, C, that will be equals to voltage across AC plus voltage across CB. Then voltage across AC is, because this is V plus and that is V minus, the difference will be once again your E, that is EMF, and see here VC minus VB. This is C and that is B. Current is going in this direction. So it means that potential, this potential must be greater than that potential. When that is greater than that one, so VC minus VB becomes minus IR. So now you can write V equals to E minus IR. This is the voltage across the battery when circuit is open. When circuit is open. So this implies, what is V? V is voltage across A and B, and that you can write down even as IR from here, IR. Then IR equals to E minus IR. That implies if you take I common, then I can be E by R plus R. If so, this is what current in the circuit. So current can be maximum if R equals to 0. If R is 0, then I will be E by R, and that is maximum current. If R is infinity, if R is infinity, then I becomes E by infinity, that is 0. So that is when you open the circuit. When you open the circuit, open circuit offers infinity resistance, so you get 0 current in the circuit. And in this case, you look at in this diagram, from A to B, current is going in this direction. This is outside the battery. This circuit is outside the battery. In this, current is going in this direction. But when you are inside the battery, current is going in opposite direction. Look at this diagram. You can find out. Look at this diagram. If you are outside the battery, current is going from A to B in this direction. Inside the battery, or you can say outside the battery, current is going from high terminal to low terminal. And inside the battery, current is going from low terminal to high terminal, or low voltage point to high voltage point, or less potential to high potential, right? And here it is going from high potential to low potential. So this is what happens. Sometimes current can also go from high potential to low potential inside the battery. So that is when you are charging a battery, then current will go in reverse direction. So current enters, or positive charges enters at a positive terminal and goes through the battery and leaves the battery at negative terminal. So that is what happens in case of charging. So here you need to understand one important point. when charges are going from A to B through the resistor, some in delta t time, if some number of charges are going through the resistor from A to B, then immediately once it gets here, immediately the chemical forces will act, and that chemical forces will bring the same amount of charge from here to here to maintain constant potential difference across A and B. So if you are able to maintain constant potential, then only you will see the steady state current in the system. If there is no for example, let us take one more problem. Look at one more situation. So there is a wire here. Let us take a conductor in the form of cylinder. So this is cylinder. Now let us take two metal discs with a positive charge plus Q here and a negative charge. Let us take two discs. One will be positive charge and one is negative charge. So disc is having positive charge, then its potential must be something plus and that potential must be something minus. When you take positive charge here, so this end becomes positive, and this end, now I am taking this charge here, so that becomes negative, because here it is having minus Q, that is having plus Q. When you attach these discs across the ends of the across the ends of this conductor, then immediately charges will go from positive to negative. As charges are going from negative to positive, the current in the circuit goes from here to there, and as charges are going from here to here, then potential here decreases and potential there increases. When potential here decreases and potential increases, here potential increases, then potential difference goes down, because the potential difference equals to V plus minus V minus. So this is coming down and that is going up. So at some point you will see zero potential. Once you see zero potential, you see no current, because I equals to V by R. So you can say there will be no potential difference, no current. So if there is no potential difference, you will see no current in the circuit. So because here there are no mechanism by which you can bring whatever charges depositing here to bring that back to here. But when you connect the same thing to a battery, as whenever charges are coming from here to here, immediately the charges will be taken by chemical forces from here to there once again to maintain constant potential. And here there is no such mechanism. Because of that, immediately the current in the circuit goes to zero. So look at this is what about your internal resistance and EMF, etc. Now let us look at a few problems here. The first problem is a battery of EMF 2 volt and internal resistance 0.5 ohm is connected across 9.5 ohm resistor. How many electrons crosses through a cross section of resistance in 1 second? So now a battery, this is the battery of EMF 2 volt and internal resistance 0.5 ohm is connected across 9.5 ohm resistance. Across 9.5 ohm resistor. Now question is, how many electrons crosses through a cross section of resistance in 1 second? So now first let us estimate what is current. So we know that E minus IR equals to V, that is IR, and here R is 9.5 and internal resistance is 0.5, and this is, let's say, R is 9.5 and small r is 0.5 and E is 2. From this data you can able to compute what is I. I is E by R plus R. So E is 2 and R plus R is, it's a 10, so I will be 0.2 ampere. If I is 0.2 ampere, then I you can write down as dq dt, and that implies dq is 0.2 dt, and in 1 second the amount of charge that goes through the cross section of area is 0.2 coulomb, because dt is 1. So this amount of charge will go through a cross section of resistance. So how many electrons will cross? So this is total amount of charge. Then we know total amount of charge equals to charge of an electron is 1.6 into 10 power minus 19 coulomb. That is the basic charge. So that implies N equals to Q by E. Q is 0.2 and by 1.6 into 10 power minus 19. So that equals to 1.25 into 10 power 18 number of electrons. So this many number of electrons will cross the area per unit time, per 1 second. Next question. A battery of EMF 2 volt and internal resistance